About 8 faculty in this lab, and of course most of the work, all the work is done by the students, so unfortunately I can't put all the photographs of all the students over there. So we mainly work on what we call computer systems research. What does that mean precisely? So it includes things like cloud computing, which has a pointer as well. There is no pointer in it. Okay. So it includes things like cloud computing, blockchains, 5G systems, even though that's sort of borders networking and systems. A lot of the SDN work, which is almost all computer systems, software systems today. A lot of multi-core architecture, GPUs, things like SmartNICs, SoC-based SmartNICs, and so on. Those are the kinds of areas that we operate in this particular group of faculty that you just saw. The research is one sort of aspect of what we do. We also try to put out as many courses as possible for public consumption through either NPTEL or there are courses on our website. You can go look at it in these areas that I just talked about. So there are courses on virtualization and cloud computing, for example, on there. There are courses on operating systems, more undergraduate level type things. And there are other courses as well. We also conduct boot camps. So this past summer we had a boot camp in systems technology. So things like DPDK, for example, where you can process network packets very fast by reaching into the NIC and picking it up, and the application processes network packets. Technology that was made popular by Intel. Things like gRPC, things like RDMA. Those sorts of technologies we had a boot camp on. We had a reasonable response to online. And post the boot camp, there were a few students who came to work with us after that as an internship. So we offer internships in this lab for students who are interested in systems work. And for those who want to go beyond that, then we work with them closely on their BTech or tech projects wherever they are in the country. Right, so that's one part of it. And then we also do consulting for various industries. We get involved with standards bodies within India for these areas in particular. Of course, 5G is a huge space. Lots of IITs are involved in that. Lots of universities, lots of other organizations, and so on. So that's sort of a three-pronged approach that we have. And if you'd like to get in touch with any of us with respect to system topics, if you're interested in it, and if you want to collaborate, we welcome collaboration. That's why I'm sort of putting up these slides. They have nothing to do with my talk. Okay. So my area of research is cloud computing, and within that, for the past couple of years, I've been looking at what is called function as a service, or serverless computing, as it's also known. And our focus is on trying to make serverless computing platforms be efficient, be faster. So fast, making faster. Again, this is all joint work. Lots of I'm going to present some work that has been done over the past 4 years or so, but hopefully, more importantly, point out some interesting open problems in the space. Right? So that's the focus on the talk. Okay, so this is like a big busy slide, but you mainly need to focus on the things at the top. I have a pointer. I think myself to have a pointer. So the things at the top are what are important. So it doesn't matter. You put that in? Okay. So cloud computing has evolved over the past 10, 12, 15 years. It's now here to stay. Many enterprises are deeply embedded within the cloud out there. And it all started as, the cloud was always there, so to speak. The private data center that existed within the enterprise was the cloud, right? It was a private cloud. Only that particular enterprise could use it, right? Whatever that enterprise be. Then people found that it was a pain managing the machines, it was a pain managing the data center, you required expertise that was not easily available, and therefore companies said we have the expertise. So companies like Amazon, which first came out with the EC2 cloud, said we have the expertise to manage these machines, we can scale, deployment of these machines to 1 to hundreds of thousands of servers very, very easily. So we offer this infrastructure, which is a machine or a part of a machine, as a service. Okay, so this was the notion of computing as a utility. So what are the typical utilities that we are familiar with? And the most common utility is probably electricity, which is driving this. We don't have a generator here, then maybe we do, I don't know, but we certainly don't generate electricity in all the places we use it. Right? We consume it as a service and we pay for what we consume. And so that was the earliest notion of cloud, where infrastructure, compute infrastructure was provided as a utility. Right? Things like CPU, things like memory, things like storage was provided as a utility, and one could rent this infrastructure on the cloud of whatever size. So suppose I want a machine with 4 cores or 8 cores with 16 to 32 gig of RAM, with some amount of storage attached to it. Maybe you wanted some SSD storage, some spinning disk storage, and so on. So the cloud provider would spin up such a machine that you specified and gave you an IP address for you to log in. That's it. Right? So you didn't need to buy the machine, you didn't need to install the machine, you didn't need to arrange the cooling of the machine, you didn't need to manage the machine, administer it, nothing. You said, this is the operating system that I want, and they just gave you an IP address, and if you logged into it, it had that operating system, and you could just use it. And when you didn't want to use it, you just turn it back and you are done. Right? So that's infrastructure as a rental service. Right? Today, pretty much everything is a service, right? So cab companies don't own, you rent Ola rather than owning a car. Right? So that's the same notion there. Now that was great, right? So for many companies and institutions, even academic research started using the cloud because they needed lots of this machine computing power. Right? So if I needed, say, 512 cores in order to train some very large neural network with tons of parameters, I didn't have to buy a 512 core machine or even machines that floated out of that. Because I only needed it for a week or 10 days or 2 weeks or whatever. Right? So in this case, I could rent it from a cloud provider such as Google or Amazon or Azure, and I could use it and give it back when my research was done. So that was the earliest sort of incarnation of a true cloud, right, which had, in principle, infinite scalability. Right? So I could write one machine, I could write 100,000 such machines. And the cloud provider said, we'll make sure that you get there for the most part. Of course, unless your request was completely unreasonable, in which case it would not happen. But then what people found that, I got a virtual machine, and this was realized through the technology called virtualization. Virtualization always existed, right? For 30 years, this technology has been around. But cloud providers such as Amazon EC2 and Google Cloud and Azure really brought this to the fore, right? So virtualization became the heart of cloud computing technology. So VMware became a wildly successful company because of this, because they had a virtualization software. But it was still the issue that, so if you, for example, had a Windows virtual machine, you still had to keep it patched, you still had to keep it protected, you still had to sort of manage it from a systems administrator perspective. Right? So that got painful. Suppose all I wanted was an Oracle database. Okay? Then I did not want to rent a virtual machine and then install the database and manage it. So platform as a service then came up, which basically provided Oracle as a service, right, or Postgres as a service. If you wanted a database, if you wanted an application server, it provided some sort of application server as a service. So you didn't have to install the app server, you didn't have to install the database, you didn't have to administer it, manage it, nothing. You could just use it, right? And this was provided to you. And the cloud provider took care of provisioning the appropriate amount of resources. So if you said, I want an Oracle instance that needs to store, let's say, 2 terabytes of data, right? And I'm going to have 300 concurrent users accessing it. The cloud provider now knew how to size this in some way. So they would say, okay, in order to do this, I need a 64-core virtual machine with 512 gigs of RAM and so on. So they translated your user requirement into some system requirement behind the scenes. And they spun up this virtual machine, they ran Oracle on it, and then they gave you an Oracle login. And then you could do whatever you wanted to do, just the Oracle login, right? So that's the notion of platform as a service. So So it provides you some platform on which you build applications, right? And that's typically how it works. So all of these applications are built on several platforms, typically databases, application servers, web servers, many other specialized servers. Today you have analytics servers like Spark or Hadoop running it, more likely Spark, and so on. So that was platform. Then before FAST came into play, there was this notion of the entire software application being provided as a service. Right? A classic example is Zoho, for example, or Salesforce.com, and all these companies. They provided entire applications, so Salesforce automated applications, as a service that could be consumed by anybody. Payroll applications are today standard services. Nobody runs payroll within the enterprise, right? Out there. Administration, HR, all of these kinds of things became whole applications. And the application that you probably interact with on an everyday basis is email. Right? Gmail.com is a service to you. You don't run an email server, it's provided by somebody else. Right? Google provides it, they take care of managing it, they take care of ensuring that the data is replicated wherever and whenever it needs to be replicated and so on. And you just consume the end application as a service. Right? In this case, email may be free. Small packages of software that are self-contained in the sense they're stateless. Right? So across two invocations of software, no state is maintained. That is what is important. Right? So I invoke it 100 times. Each time I have to give it the input for it to process. Right? So it will take an image, it will spit back, here are the faces are recognized. And that's it. It won't remember that invocation for the next time. You give it another image, it will again recognize faces and give it back to you, and so on. Right? So these functions are then composed into some sort of image processing application. In our case, the crime detection application that we want to build. Right? So first I have to take a video. I have to sample frames within that particular video that I'm getting in some intelligent way. I don't have a sampling function, but it's there, assuming there is a sampling function there as well. So once I detect or once I sample the functions appropriately, each one of these frames that I have sampled has to be given to, first I will sharpen it, I will change the contrast of it, I will give it to a face detection piece of software, I will then give it to some gate detection and so on. Then I put the results of them together in some which way. Right? So that's what happens, that's what a composition is to make an application. It is nothing but a workflow. I will first scale it, I will blur it, or if I blur, I'm not actually blurring the image, but I may be anti-blurring it or whatever. Right? So it will be sharpening it. Then once that is done, I can do face detection, pose detection, and feed detection all in parallel. That's what it is trying to say. So there is a sequence, scale, blur, then I do process packets in hardware significantly faster than transferring the packet through the operating system kernel to an application for it to do something. Right? So NICs today are very sophisticated devices. They have the ability for you to install programs on the NIC. Right, using some special purpose languages, P4 is a common language for this, that will then enable fast, inline, network level processing of packets that are coming. Right? And everything is a network packet at the end of the day. Right? If you send a HTTP trigger to some site, it's nothing but a set of network packets. If that can be processed on the NIC instead of the computer having to read it and process it, the processing is going to be much faster. That's the basic idea. Right, so there is another trend which I'm not going to discuss right now, but persistent memories are also sort of becoming popular. Okay, so I am particularly interested in the GPUs and the smart NICs for the remainder of this talk. Then, so many things, right? So the evolution of cloud computing and what FAS is or serverless is today. Second thing is how software architectures have evolved in order to be structured as a set of cooperative microservices or a set of functions, right? Workflow of functions. And finally, some hardware improvements. So these are all three distinct things, but how do you put them together is the real question. And that's what I'm. Yes, that's my outline. I don't know how. Somebody needs to keep track of time for me. I don't have a clear what form or anything could be, huh? Okay, so till what time do I have? Okay, 1:20. So I'll try to go at that pace. But stop me anytime. So I talked about that and how functions can be deployed by developers and triggered to be executed by end consumer. Right? So this face detection function. I send an image, you tell me, does it contain a face of somebody's event? Simple function, right? And Google image processing, any image processing, right? This or Flickr, all of these kind of applications can use such things. So in fact, today on your phones you'll notice that there is face detection software already. Right? You can tag people's faces or animals' faces or whatever it is that you want. And then later it will use the tag to detect the same person or animal or thing or place in other photos. And it will tag all of them as well. Then it will say, you want to see other photos of this person appearing in. And that's already available on today's phones. Right? So sophisticated stuff, but made possible by these functions. It's actually going to the cloud to make it happen right away. It's not all happening on the phone at all. The phone is sending an image to the cloud and asking it if this image had the tag of this person, and here are the 100 other images, how many of them contain that person? That is being run in the cloud as a function. So when a function, let's say a function is already deployed. I'm the developer, I do face recognition function, I deploy it into the cloud. Now you are the user, end consumer or the user of such a function, and you want to send an image to the cloud for it to recognize some face. Right? This is called a trigger. Right? I will send a trigger, and along with it I will send an input, which is the image that I am going to ship. Now what happens when this image actually hits the cloud? This is the first question. Right? How is this taken apart? This is where the fast platform comes into play. What happens is that the cloud provider has recognized that a trigger is coming in. The trigger is meant for this function, the face recognition function, and that's sitting in some database somewhere. Right? The cloud provider has to spin up an execution environment to run the code for that function. Right? So this is typically a container. Right? Everybody knows what a container is. Virtual machine container. A container is a lightweight virtual machine. Let's think of it that way. It's fast to spin up compared to a VM. A VM may take a minute to come up because it has to boot an operating system. A container relies on an existing operating system, so it will spin up in a matter of 500 milliseconds or so, half a second is what it takes for a container to come up. Once the container is up, the code for that function is injected into that container and the instruction is given to run it. And along with it, the input that has come from the user is supplied. This is the sequence of events that occur for that function to be executed. And of course, once it's executed, there's some result, and the result is returned back to the user. Very straightforward, right? Now, all this takes time, right? So, for it to recognize that this is a function, pull the function code out of the database, start a container which takes half a second, inject the code into the container which takes another 100 milliseconds. All of this takes time before the function starts executing. Function code starts executing. First line of code of the function executes probably after 700 milliseconds or 800 milliseconds or whatever, once the trigger arrives at the boundary of the data set. Right? That 700 milliseconds may not be acceptable. That's the point I'm trying to make. Right? So this is what is called a cold start. A cold start is an executing environment doesn't already exist for that function to run. An execution environment has to be spun up, and then the function can be run. And the time that it takes for that execution environment to come up in the platform is what is called a cold start time. And this is just wasted time because nothing is running at this point. Okay? And this adds to the overall latency. Now, when there is one function, a cold start overhead is maybe 700 milliseconds. If you have a workflow of such functions, where I have to run say 10 functions one after the other, every function that workflow will suffer from a cold start potentially. Right? There is also something called a warm start. I'm not going to discuss that right now. But this cold start overhead that I pointed out cascades across the set of functions if all of these functions must be fired off in some linear sequence or any sequence, or essentially one after the other. If you do that, then there is a cold start overhead for function 1, cold start overhead for function 2, and so on and so forth. Right? So if you have a linear sequence of 5 functions, then you have 5 cold starts overhead before the workflow will finish executing. Right? So this is something multiplied by 5 is obviously bad. Right? So if the function execution time itself is some x, then let's say it is 2 seconds is what it takes to execute these 5 functions. Right? 400 distributed to whatever, doesn't matter how it's distributed. It takes 2 seconds to execute the workflow if everything is ready to be run. Right off the bat. If everything is not ready to be run, I am going to pay an additional overhead of maybe 3.5 seconds because I am assuming 700 milliseconds per function for a cold start. So I'll have to wait. So if my overall latency of the execution of the workflow is 2 seconds, I'm really going to get back the results only in 5.5 seconds in this particular case, right? Assuming these numbers. These numbers of course will change depending on the function. Right? So this is what is called a cascading cold start problem in functional research. Right? The more functions that you have as part of the workflow, the bigger the problem it becomes. Right? For the cloud provider to ensure some sort of response time or responsiveness to a trigger that showed up for a particular workflow. And that's a problem. So how do you deal with it? It's a question. Right? It also turns out with some real data. So Microsoft from the Azure cloud about 5-6 years ago put out data on millions and millions of function executions that we're doing. Right? So consumption by researchers like us. So we don't have access to this data for our production setup. Otherwise, so we took a look at that data set, and both Amazon and Microsoft has put out data sets like this in the past, and we found that a very large percentage of times this cascading cold start problem actually occurs. Which is when it is important to solve the problem. Two conditions. One is the problem itself is big enough that it is worth solving. If I had a 50 microsecond overhead for a 3-second function, I may not. The overhead has to be sufficiently large that now as a researcher I am interested in solving this. The overhead also has to occur sufficiently frequently as a researcher I should be interested in solving. If this overhead occurs once in 100,000 functions, okay. Right? Pay the overhead and get on. But it doesn't. As it turns out, this overhead occurs fairly frequently and it's of reasonable size. As a result of it, it is a problem worth solving. Like any other research problem that you have. So, how do you solve this? Is the question. So we know that the overhead occurs, and we know it is fairly frequent, and we know the reasons why it occurs. The reasons is because you have to spin up a container every time a function trigger occurs. So what if we spun up all the containers of the workflow up front? This is the first question we ask ourselves. Right? So let's say there are 5 functions of the workflow. We know it's a workflow. Right? The schema has been given to us up front. So if there are 5 functions in the workflow, and the first trigger for the workflow arrives, we spin up containers for all the 5 functions right away. Right? We inject the code, we keep it ready. And now only the first function now suffers from the cold start code. The first in that sequence of functions will suffer because as I spin the first container up, I spin the other 4 also and keep it ready. Right? And therefore when the first function is done executing, it sends a trigger to the second function, but that's already ready to go. It's there. Right? So I can just start executing immediately. That was our first idea. Right? So we said, let's pre-deploy resources. Right? As the function, the trigger comes in for the workflow, I will deploy resources for the entire workflow upfront and keep it running. And as the workflow progresses, the resources are ready, so it will not have to wait at any other point in time. Only the beginning has to be made to wait. Right? So we did that. What's the issue? That you would see. Now I'm going to tie up a bunch of resources from the beginning to end of the workflow that are needed at various points in time within the workflow. Which may not be a good thing. Right? So if I tie up, let's say, 4 cores and 16 gig of memory for each function, now I have tied up 16 cores and 64 gig of memory for the period of time that all of this has to execute. Right? And resources are precious. It's like an airplane. Right? An airplane should always be in the air carrying pattern. If you are sitting on the ground, you're losing money. Yeah.
So since it is in network, multiple users are there, resource is limited. So another is when more requests will be there, then there could be some constant processing the thing. So timing will be help.
It will be. It depends on availability of resources and the load, current load on the environment, and absolutely it will vary. I am taking the case where there is no such issue. That's the simplest possible scenario, right? The more load I have, the more I may have to wait to provision the resources. Yeah, so there is a queuing time. Absolutely. But this is, without all of that, we still have one. That's what I'm talking about. It is the very simplest incarnation of this problem. So, what I was saying was that we can pre-deploy resources and it prevents the cascading code starts of every function in the sequence beyond the first function, but it ties up resources upfront across the workflow execution time. And that's not good, right? If you tied up these 16 cores and 64 gig of RAM for 5 seconds, it's worth a lot of money to the cloud provider. It may not seem much to you, but for the cloud provider, where this is happening very, very frequently, it is worth a lot to tie up these resources with the time. So that's not good. So the question is, how do we get around that, right? So if application runtimes, so function runtimes can be predicted with some degree of accuracy, then the argument that we made was that you do just-in-time deployment of resources. Right? So let's say there is function 1 through function 5 in a straight sequence. Right? That's the simplest case. We know that function 1 takes, let's say, 1 second. Right? Once it starts, I know that 1 second later, function 2 is going to require a continuum of the appropriate time. Right? Which means if the container takes half a second to spin up, right? Then half a second into the execution of function 1, I can start the spin off of the container for function 2. I don't have to do it up front. I will wait. Wait for just as long as is required based on the execution time of the functions themselves. Right? And then spin up the next container and so on and so forth. So I will cascade that spin up as well, but I won't do it so late so as to make the functions wait. I won't do it so early that I'm wasting resources tying them. So somewhere in between is called just-in-time deployment. And if you can do a good job of predicting runtime for different functions, then you will do a good job of just-in-time. And that's the thesis here. And now prediction methods are getting better and better. Right? So the more functions you run, the better you're going to get at prediction. In some way, it is dependent on a set of factors, let's say input size, things like that, branches that it takes, and so on. But that's the idea, second idea that we put in and we solve this. There's one last problem here with this. Workflows have branches. Right? So it can be that I execute function 1, function 2 in a sequence, then ask the question, what should I do next? Depends on the outcome of function 2. Or maybe the outcome of both function and function 2. Whatever, right? It's like an if branch in a program. Exactly the same notion to it, right? An if branch in a program, some branch is taken, we don't know what. And that depends on what the conditions are, what the states are at that point in time that the branch is hit. And based on the states, some branch is taken. Same notion in workflows, right? Function 1 is executed, function 2 is executed. And then a question is asked, what should I do next? Should it be 3 or 4 or both? In such cases, deploying resources, I don't know what to deploy just in time. I don't know which branch will be taken. Will I take the left branch and therefore should I deploy the container for the function associated with the left branch? Or should I do it for the right branch? That question now can be asked, right? Or I can do it for both. I can do it for both and waste some resources. All of these three are options. But if I can somehow predict which branch will be taken, this is almost exactly similar to prefetching instructions in code in architecture, in CTS, for example. Right? So for those of you who are familiar with architecture, it's almost exactly the same thing, but we're doing this at the level of software in a fashion. Right? So that's the third idea. So if you can figure out ahead of time what the branching is going to look like, and where you're going to branch off left, where you're going to branch off right, in what conditions, then you can predictively spin up resources for those particular branches. and therefore you have the best, fastest environment, so to speak, for cold start, solving the cold start problem. So these three ideas we put together and we wrote a paper on this and we sent it to work. So it was accepted in middleware. So I'm not going to go into the details of how we did this. But if you take a look at some of the benefits, it's fairly obvious. So if you take, so just the terms here, Knative and OpenWhisk are open source fast platforms. Knative from Google, OpenWhisk from IBM. Right? So these are standard fast platforms that are already available. Xanadu is what we wrote as part of this effort. And Xanadu with different variants. So the JIT is the just-in-time deployment of resources, and speculative, which we expect to be the best. I mean, without wasting too much resources, speculative says, with my banking prediction being accurate, how well can I do? That's the question that I'm asking. Right? So this is just in terms of latency overhead. This graph is showing in terms of latency overhead. So if you take a look at the standard platforms like OpenWhisk and Keynote, you'll see that linear chains, your latency will increase linearly because the code starts. But with our platform, Xanadu, which is the blue and the red lines, then you can sort of keep it down to a very minimum in terms of overhead with increasing sizes of the chain itself. So there is some results that shows that what we did was right, which is what everybody shows in our case. But they never show how what they did was worse. And this is in terms of the overhead of CPU and memory in particular, because these are the two hot commodity resources in a cloud typically. And we show that with speculation we can just be a little more expensive than what it would be otherwise. Right? With the cold start, compared to the cold start. Okay, any questions so far? So this software is available at this Git site. You can download it and use it if you want to. This is Xanadu software. And it was also published in a paper at IEEE Middleware in 2020. Any questions on this? Yes.
So you said this is somewhat similar to the instruction sequence.
Yeah.
Apart from the level at which we need to resolve, any difference of the algorithms?
So what we do is we build the way we actually look at this ranking probability is all conditional problem. So assuming that the first branch is taken, so we build this incrementally, right? So one of the questions here is, okay, you're building it incrementally, how many runs will it take before it stabilizes to the actual path that is going to be taken? And that is one of the costs of this approach, right? So even in CPUs, what happens is you can prefetch an instruction thinking this is going to be executed, and it won't. And you just pay the price for the prefetch that you're listening to. But here, the workflow sequences can be very long. Right? So you can have 100 forms in the workflow sequence, and there can be the 5 branches, which means there are many paths within this graph. And so it's not just a matter of one instruction being prefetched and missed. But if you miss something upfront, then the whole path you miss, and therefore you may successively keep mispredicting. Right? Suppose you predicted B1 is the B2, and you took B2. Right? From B1, you're not going to reach C3 at all. Right? So that misprediction cost will cascade in the way. That won't exist in C3. Yeah.
So most likely about this definitely is there may be some resources that may be on-demand resources.
On-demand would be whatever the function needs. So if it wants to allocate memory within it using a malloc call, we'll do that. That's not what we don't worry about that. So we worry about, so the function is, so the way it is done is that a cloud provider, given a function, will size resources. Right? So today's state of the art is that you as a function deployer must size the resources. So when you give a function, you have to tell Amazon, I need half of this containers. Right? Now there is recent research that is showing that they can predict this themselves. But it's not in production technology. So this is research. But yeah, so you have to size it. That size of the container is what is used. That's what I'm counting as resources. Right? And typically that size will include any mallet calls and stuff like that. So if I say a container needs half a gig of RAM, that is dependent on what it is going to allocate. Typically that is size of the worst case. Because it depends on inputs. If I give an input array of 100 elements versus a million elements, it's going to be different in size. But so the developer will size it to the worst case in some way, some average or something. But containers are flexible, they can expand at runtime. And there may be some hold. If it is going to flexibly expand at runtime and there are no resources right now, I may have to hold it.
As a spin-off from Argo, is it possible to get some data so that you can define some patterns?
Yeah, sure, absolutely. So that's our next sort of goal for something like this, and if somebody is interested in working on it, the source is available for the network. So using ML, for example, to predict, we've not done that in this particular paper. Yeah, everybody wants to do some ML. Not just ML, right? I mean, it's there to add ML, like AI, whatever it is that you want to add. Yeah. Yes. Yeah. It's also possible. It depends on the workflow itself. So the workflow structure will allow parallel processing. But sometimes the sequence is necessary, right? So there are all these constructs, branching constructs, there are parallel fork and join constructs, there are just sequential constructs, all of that exists. Okay. So I'll just very briefly address this part of it, which is a smart NIC. So far I have not really addressed the intersection of smart NIC, GPU, nothing. Right? So remember what I said at the beginning of the talk. But I have not. The question is, what makes this orchestration flow? Orchestration is really the notion of saying, where am I in the workflow execution? Right? So the workflow execution has 20 functions. I have done the word one, and now I have to realize what to do next. Right? I have done 1, 2, 3, and now I can do 4 and 5, either parallel or sequentially, whatever. It doesn't matter. That depends on the schema of the workflow. That is the notion that is called orchestration. Orchestrator, just like an orchestra conductor, is saying, you do this, then you play this, and then you play this. The same thing. And that's what an orchestrator does in fast environments. It says execute function 1, when you're done, execute function 2, when you're done, execute 3, 4, and 5 in parallel, when you're done, etc. That's what. Now, it turns out that this is where the NIC comes into play. Right? So the function trigger actually arises as a HTTP call. What's the HTTP call? Nothing but a packet traveling over the internet somewhere. Right? And it arrives on the NIC of the computer. So the dispatch system is a computer, is a server. And the worker is a computer where the container is actually run. They can be different. They can be the same, but usually they are different. That's why. Right? And each of these computers, the dispatch system, the worker, have a NIC associated with them. Right? The packets travel to the NICs and reach the computer. Now, as you see, the first function that it comes to, let's say the function trigger comes in for the worker. That is 1. It travels through the NIC to the dispatcher. Dispatcher now realizes that I have a dispatch function 1 within the workflow. Right? So that is 2. It sends the call, that goes back to the NIC for the dispatch system, goes to the NIC of the worker system. That is then 3 goes out to the worker. Right? Now the worker processes the packet and it says I have to run this container. It will run it. Run the function, the result is sent back to 4, comes back through these 2 NICs, goes up to 5 to the dispatch system. Now the orchestrator kicks in and says, aha, function 1 is gone. What do I do next? Is the question that it asks. Right? So you see that there are 6 calls that traverse the network for just one function within the sequence. That's the problem. Right? This traversal cost going from the NIC to the dispatch system is approximately 300 microseconds. microsecond. It's in microsecond. But what is a traversal pass composed of? It is actually composed of multiple copies from the NIC to the kernel, from the kernel to user space, and so on. Right? So remember, the kernel has a role to play in the network stack. Right? It unravels the network stack. The IP headers, the TCP headers, HTTPS headers, all of this has to be stripped, and the actual data is passed on to that takes time. So what if it takes time? It's for 300 microseconds. What's the big deal? Is the question. Right? So we'll take an example. Twitter. It's a bad name today, but still, Twitter is Twitter for work purpose. Right? So Twitter used to get about 6,000 tweets a second, approximately. That was the workload that they were seeing. We got some real data that has been published. Right? Now each tweet has a workflow processing in a function as a service manager within Twitter. Right? So each tweet has about 11 to 12 functions in that workflow behind it. It does a whole lot of processing, it does sentiment analysis, this thing, that, all of that stuff before the tweet is published. So this turns out to be about 70,000 triggers per second, for 6,000 tweets a second. Right? 70,000 triggers a second. So end-to-end latency demand for this workflow is about 10 milliseconds. They want to finish this whole thing in 10 milliseconds. Remember, that's their target. Now, if you take a look at these dispatchers, it turns out that the actual dispatcher itself, just the act of saying, go run this, go run this, go run this, go run this, somewhere, wherever that be, not the running of the function, the act of dispatching itself is expensive enough that it will saturate at about 4,500 requests a second. You can't push the dispatcher beyond 4,500 requests a second, and it's not meant to scale horizontally. That's the unfortunate problem of dispatching. Right? It doesn't scale horizontally, it has to scale vertically, and only take up 2 or 3 cores to take a look at OpenRest and Keynote. So all three, we look at Xanadu, which we had written in the previous paper, and these 2 open source instructions, all of them saturated at this level. They cannot push more than so many requests a second for worker space. And that's a problem, because we're looking at 70,000 requests a second. And the latency of the dispatcher itself shoots up to something that is very small, to something that becomes abnormally large at that 4,500 requests a second. It is almost a second, 2.7 seconds for dispatching itself, which is ridiculous. Right? If they have a 10 millisecond end-to-end latency requirement, and your dispatcher itself is taking 2 seconds, nothing will get easy. So that's the problem we set out to solve in this particular system. And this orchestration overhead of network traversal of the 6 things that I showed you earlier is about 300 microseconds. Right? And we could not really deal with that, and this is what I'm not going to go into details with this. Right? So this is the thing. So what we said was that the way that this dispatch is being done, is figure on the left. Right? There is a request queue into which all the packets are coming in. Then there is an event loop that is DQing packet by packet. This is why it does not scale automatically. And then there is asynchronous thread for servicing the particular packet, and so on. Right? So this is how the dispatching actually gets done. And the dispatcher code is involved as the 4th part of that particular process, as this. Right? And with load, we know that this does not scale at all. So the question we asked ourselves was, can we do this on the NIC, a smart NIC, not a regular NIC won't have a capability. What is a smart NIC? Right? Very briefly, this is what a smart NIC looks like. This is one type of smart NIC. There are many types of smart NICs available today. Right? This is what is called an ASIC-based smart NIC, which can be programmed. So this it looks like a small computer, as you can see. Right? The NIC itself looks like a small computer. It has a bunch of RISC cores. Right? It has what is called a match action table, which in hardware will do that event loop for us. Right? That we talked about earlier, which is being done in software. And there's some small amount of memory associated. Right? It's not like a regular computer which has enormous memory, powerful cores, no. Right? You can either get ARM cores or some RISC core. It can do small amount of processing. But it is done on the edge of the network. You don't incur the 300 microsecond overhead to push things out to the user space and for it to make a decision and then to come out. That's what we say. And because the dispatching is being done in hardware, right, it can scale to 10,000 requests a second or more. Remember that 4.4K that we saturated at, this can be pushed not 10, about 100,000 requests or more. It can be done in a second on the NIC hardware for a specific NIC that we experimented with. Right? So it's called the metronome Bellur, and that has this kind of architecture inside. Right? So this is the basic idea. I'm not going to go into the detail of how we achieved it for the interest of time. Basic idea is that we offload the dispatcher onto the smart NIC and make the decisions close to the network where the packet is coming in, as opposed to using the user space dispatcher. And this idea can apply to any system software. Right? We are doing it for fast. Doesn't mean you have to do it for fast. We have also done it for file system metadata handling, for example, is another project, and it gives equally good results. Right? So the basic notion of offloading some small amount of computation. It can't be powerful computation because the scores are not powerful. Right? So if there's some small computation that is repeated very, very often, you can then offload that to the NIC and make it scale tremendously. That's sort of the bottom line of this. I'm not going to go into details. Again, this is another paper that was published at SOCC, a conference called SOCC. These are all details. If you are interested, come and talk to me after. And you can see the scaling capability of the latency scale almost flat at 90 microseconds or so. Yeah.
It is supposed to be more of a caching data.
No, it's not.
You also put it processing page.
No, we don't. So we have done experiments where we vary the rate of incoming network packets, which is, so the NIC has two jobs, right? One job is it has to process network packets, which is coming in a regular thing. So there may be another process running in the host which requires network packets, some web server or something like that. So NIC has to still process those network packets. There are separate cores that can be assigned to them to say that they won't affect the things. And you can scale the number of cores given to the additional computation that we are now offloading to the NIC up and down depending on the network traffic that is coming. So that you don't affect, you're right in the sense that you should not affect the network packet processing capability of the NIC. And so that's an important problem for us. And so you have to scale the offloaded computation up and down, right? And in fact, an open problem is when do I say stop using the NIC for this and push it up to the host and let the host take care of it, all of it. And when do I take it from the host to the NIC and take back to the host? This is a very interesting open problem. Okay, so I'll. Unfortunately, I have some other stuff I don't think I'll be able to cover, so time, running out of time. So if you have any questions on work that I've discussed so far, I'd be happy to answer it. So this is a paper, it's called Keynote. This was published last year in SOCC. And we have code for this from CSC. One the code that we have to give you. So I don't have time to talk about GPUs and a whole bunch of nice open problems for researchers to get involved in. But if you come talk to me, I can I'll partner with something. Anytime. And we'll be happy and welcome collaborators on work like this. Hopefully give you a sample of the kind of work we do. And of course looking for collaboration. Work with us. Thanks. Yeah.